Hey everybody. Today I'm doing an example of logistic regression using R. I'm going to be looking at the classic iris dataset and attempting to classify flowers as either setosas or not setosas using just the length of their sepals. I've already loaded up tidy models. That's going to bring in several packages that I need. I'm not going to do a full-on tidy models treatment of this today, but I do want a few of the functions in there. In particular, I'm going to be using the R sample package to do my testing training split. Loading up tidy models also gives me ggplot2 and dplyr, both of which I'm going to be using. Right off the bat, I'm using dplyr here. I'm going to add a column to the iris dataset called setosa, and it is just going to be a 1 if the flower in question is a setosa and a 0 if not. So species equals, quote, setosa is going to be trues and falses. Then I've added as integer so that I get zeros and ones. This is going to make that dataset play nicely with my glm command in a little bit. So let's execute that and take a quick look. There we go. Classic iris dataset, 150 entries of irises, I believe in Nova Scotia. And now we have ones for setosas and zeros for versicolors and virginicas. Great. So in this video, I actually want to build the model on one set, a set of training data, and then evaluate it on another set, a set of testing data. And so I am going to split my data into two pieces, and I'm going to use 80% for my training set, 20% for my testing set. I'm also going to stratify it by setosa. That's that binary variable here that I have, so that I get equal proportions of setosas and non-setosas in both my testing and training set. So it should be about 2/3 non-setosas in each one. The initial split command is in the R sample package. It makes this pretty easy. So split is then just going to have the characteristic that the data set is being split into two pieces. And then I have made two sets, iris train and iris test, that are actually going to consist of the 80% for my training, the 80% of the rows for my training set, and the 20% of my rows for my testing set. I guess we could just look at iris train really quick. Did I not execute this? I didn't execute this. There we go. So this is exactly like the set we just looked at, except now this one only has 120 entries. The other 30 are in the iris testing data set. Okay, great. So I want to start by visualizing my data. It's always good practice when you can, when the data permits it, and when your time permits, to visualize your data before building a model, for lots of different reasons. First of all, a visualization lends insight on its own, and it can be useful both for you as you understand the data, but then also potentially for people you need to communicate with later on. Secondly, by looking at a visualization, you can tell if the model you have in mind is even plausible for the data, whether or not the sorts of assumptions that are required for that model might possibly be met. So I'll do that with ggplot, and I think I'll just look at iris train. And for my aesthetics, I want the explanatory variable on the x-axis, so that's going to be sepal.length. I'm only going to use one explainer here, although there's several others that I could have used. Sepal.width, petal.length, petal.width. I'm just doing a simple logistical regression right now. An open question here is, which of these variables are the best explainers? Which combinations might be better? And for y, here I just want setosa. So that's going to be a binary result, so zeros or ones. And, I did this plot as I was writing this video, writing the script for this video, and there's a lot of overplotting. So instead of doing geom point, I'm going to do geom jitter with a height of 0.05. And I did this just through trial and error, just through trying some different values. And let's have an alpha of 0.05, or 0.5 rather. So that'll give me a little bit of transparency. Let's see how that looks. I'll zoom in on it. Okay, so we again see sepal.length going left and right, setosa going up and down. Obviously, setosa is either 0 or 1. plus and minus a little bit of random noise that I've allowed to be added here. And you can see that this is a good candidate for a logistic regression model. When sepal lengths are small, there's a high probability that the flower we're looking at is a setosa, and as the sepals get longer, the probability of the flower being a setosa drops down until it's finally asymptotic towards 0. So let's go ahead and put on this characteristic logistic curve that we'll be expecting from our model right now. So I'm going to add a geom smooth. Method, well, I'm going to be using a generalized linear model, so it's method GLM. And I have to specify what kind of GLM I want, which means I need to pass some arguments to the GLM function that the smooth command, the geom smooth command, is using to put on the smoother. Now, at the beginning of the day, R doesn't know if I'm going to need to pass 1 argument, 2 arguments, or more than that, so I need to pass the arguments as a list. The syntax is method.args equals list, and now I can put the name of the argument I actually want, which is family equals quote binomial, because there's a binomial response here. And let's go ahead and leave out that standard error ribbon. And while I'm at it, let's get rid of that gray background with theme minimal. My preference. Okay, there we go. So this visualization is reasonably attractive. Looks like it's a good candidate for a logistic regression model. So let's build that model. Build or fit that model. And before we do this, let's actually take a moment to quickly review what exactly a logistic regression model is. I have a nice slide for that. Took a few minutes to make this for you. I'll throw this on my GitHub page along with the script that I'm writing. I like to show my work when I can. A logistic regression model is modeling a binary response. Call it y. So in this case, y is the setosa variable. I'm going to do a single quantitative explainer, just sepal.length, but there's nothing special that says you have to just have one quantitative explainer. You can also have categorical ones using dummy variables, and you can have multiple variables in here just by adding additional terms to this systematic component. So the systematic component is the equation of this curve that we were just looking at, right? We're actually wanting to find this. And that equation is going to be modeled by this formula. Logit P, where P is the probability of being a success, a setosa, is a linear model, beta naught plus beta 1 x. Logit is the natural log of P over 1 minus P, or really any other log, it doesn't matter. And again, that gives you the best fit here. But then, of course, we don't actually expect any of these values to be, since their values are all going to be true or false, 0 or 1, we don't expect them to actually be equal to P, which is always going to be strictly between 0 or 1. So then we get the actual value out of this model using the random component. And the random component just says that the y values for that specific x are going to have a binomial distribution with probability of success P and 1 repetition. So these are Bernoulli trials is what's going on here. So we fit these coefficients using maximum likelihood estimation, but we can't really do that by hand even if we wanted to. The maximum likelihood estimator doesn't come out to have a closed form. You're doing an optimization problem using multiple variables, both beta naught and beta 1. So you're not able to do that using just a pencil and paper. So we'll do that with R. Let's go ahead and do it. I'm only going to make one model in this vid, so I won't give this model a very interesting name. I'll just call it model. And the GLM command is actually going to be really reminiscent of what I did with my geom smooth up here. Geom smooth is inheriting these two aesthetics. So I'm going to specify my y variable, setosa, as explained by my x variable, sepal.length. And I need to specify my data set, of course. This is iris train. And then I need to say what sort of generalized linear model I want. And so that's family equals, quote, binomial. go. And well, let's use the summary command to see this. And we get a lot of information here. I'm not really going to talk about deviance. I have a whole video about deviance in logistic regression models. I'll throw a link to that up top. I'm also not talking about inference in this video, so we'll ignore that as well. Really, all I want to talk about are these two coefficients. So what they're calling intercept here is an intercept on the logit scale. So it's not actually going to have anything to do, or isn't exactly going to be the intercept on this plot that we're looking at here. Similarly, the negative 5.4 is not actually a slope for sepal dot length on this plot. The slope here is going to be variable. It's going to be the slope on the logit scale. What we're really being given here are the beta naught and beta 1 in that model form that I just showed you. So let's take a second and take an actual look at that model once we plug in those two variables. And I made another slide for this. So beta naught is 29.2 and beta 1 is negative 5.4. So our model is logit P equals 29.2 minus 5.4 times sepal dot length. Now, it can be sometimes helpful to have just written just P is some function of sepal dot length. So let's take a second and do that. As I mentioned, logit is the natural log of P over 1 minus P. And now we just do a little algebra and invert it. And once we do that, we get this thing. P equals E with the exponent of that linear equation divided by 1 plus E with the exponent of that linear equation. And if we actually plot this with Y instead of P and X instead of sepal dot length, we'll actually get this S curve that we already saw. So this is actually the equation of that line, or that curve. It's actually our model. Fabulous. Now, this allows us to make predictions for new observations. So, for instance, if we have a new iris that has a sepal length of 5 millimeters, well, we plug that in for sepal dot length here, do the math, and get a value out. And in this case, the value that we get out for P is about 90%. And if you look at this plot that we generated for a sepal length of 5, that's saying that we have a Y value here of about 90%. And from this plot, you can believe it. That's saying that if we have a new flower whose sepal length is 5, that there's about a 90% chance that it will be acetosa. All right, so let's actually evaluate our model. So, and I want to do this on the testing set. We could do everything we're about to do on the training set as well, but it would give a rather optimistic picture. These coefficients, beta naught and beta 1, were specifically chosen so that we would get the very best fit possible, the most successful classifier on this data. And so on the training set, this model is likely to be overfit. It's going to paint too rosy a picture. The analogy that sometimes gets used is that if you apply your model to your training set, it's a little bit like asking your mom how you look. You're going to get a very nice answer and get a rather rosy picture of your own appearance. So let's actually do this on the testing set. So what I'm going to do is take iris test, and I'm going to add some new columns to that. First off, I want to add a column with the predicted p-values. So let's see here. Let's call this setosa prob. And there's several different ways that I can get the probabilities here. I'm going to use the predict command. Fitted.values is another. And I need to predict using this model on the iris test data set. And I want to let R know that I would like the outputs to actually be probabilities. I don't want them to be on that logit scale. So what I want is type equals quote response. Okay? So that'll give me a column with probabilities, but ultimately I'm going to want to make some classification decisions. So let's add another column called setosa predict, setosa pred. And I would like this to be 1 if this probability in this column is over 50% and a 0 if it's not. And there's lots of ways to do this in R. I will use the if-else command. We need to say a logical statement that'll either be true or false, and then the output if it's true, and the output if it's false. So let's see here. I want to be looking at setosa prob, and I want to know if it's bigger than 0.5. And if it's bigger than 0.5, I want to output a 1, and if it's not, I'll output a yes. So let's take a look at this. Let's view iris test. All right, so we have 30 rows here. That's 20% of our original data set. And in addition to all of our original variables in this set, we have setosa, 1 if it's a setosa and 0 if it's not. We added that at the very beginning. Setosa prob, that's the p-value, the p that is predicted by this model that we just built. So for instance, this first row is assessed by our model to have a 93.6% chance of being a setosa, and so it's being classified as a setosa. This fourth observation, on the other hand, only has a 49.5% chance of being a setosa according to our model. So with a cutoff of 50%, we're saying this is not expected to be a setosa. Fabulous. So let's see how we did by getting a confusion matrix on this. I'm going to do it with the table command, although of course there's many ways of doing this. And I want to look at the iris test data set. And the first thing I want to think about is whether or not it's actually a setosa. And the second thing I want to think about is whether we predict it to be a setosa. So these are zeros and ones, these are zeros and ones. We'll get a 2x2 table. This is our confusion matrix. So the fact of the matter is in the rows. So here we have the things that are not setosas. Here we have the things that are setosas. And the prediction of our model is in these columns here. So it's not predicted to be a setosa, and it is predicted to be a setosa. Let's check our accuracy rate. And I think the way I'm going to do this is by saving the table as t. And let's get the sum of the diagonal elements of t and just divide it by the sum of t. So the sum of t is going to be 30 because I know there's 30 observations in there. So what? 25 divided by 30? About 83.3%. And that's our accuracy rate on our testing set. So this is how our model is performing on 30 observations that were not used to build the model. If we were to do all of these calculations on the training set, we would expect to get generally a higher number because of that overfitting phenomenon that we talked about a little bit ago. All right, I think the last thing that I want to do here is to calculate a few other measures that could be useful for assessing this model using that confusion matrix. And I want to start with sensitivity. So the sensitivity in this case is going to be 8 divided by 10. So that is the true positive rate or sensitivity. So sort of when you have a positive, what's the probability that you're actually detecting it? In this case, there are 10 positives in this data set. We've detected 8 of them. So this is measuring sort of how sensitive our test is to whether or not the thing that we're looking at is actually a setosa. Complementary to that, 2 out of 10, is going to be the false negative rate. So 20% of the positives are classified as negatives here. Unfortunately, those are false negatives. Not ideal. We can also talk about the true negative rate. So in this case, we are now looking at the top row of our confusion matrix. So we have 17 true negatives out of 20 total negatives. So that's the true negative rate, or sometimes called specificity. And then finally, complementary to that, 3 out of 20 is going to be the false positive rate. Let me get a comment in there. False positive rate, type 1 error rate. All right, I'm going to stop there, though obviously there's a lot more I could do with this example. We've got several other variables in this data set that we could mess with. A lot to be said there. A lot more that we could do with this confusion matrix. Sensitivity and specificity are not the only two measures. And another thing that I didn't talk about at all was anything to do with inference or variability in these coefficients that we got from R. We didn't talk about standard error or these p-values that we have. Similarly, we didn't talk about dispersion in our binomial family. We didn't think about whether or not our binomial distribution here might be over-dispersed or under-dispersed. And we didn't talk about deviance at all in this one.